Now that we've built a foundation for SLAM, we can talk about 3D reconstruction. 3D reconstruction is the process of capturing the shape and appearance of a scene or object. 3D reconstructions can be created through a variety of different technologies. In the case of the reconstruction here, we used a sequence of RGB and depth images, estimated their relative poses using SLAM, and generated the 3D reconstructions by projecting the points from the images back to 3D space. Google Earth recently started adding 3D reconstructions to its views of the world. Using many observations of the same area, the 3D position of all the points can be derived and a 3D reconstruction created. In general, 3D reconstruction comprises of the following parts. First, you need some sort of point cloud data. This could come in the form of a sequence of RGB or depth images from a camera, or a 360-degree LiDAR data from a 3D scanner. Depending on the type of data, additional steps are required before any sort of 3D reconstruction can be extracted. For instance, given a sequence of RGB and depth images, steps have to be taken to find the relative position of all the images. Next, we need to perform integration, or merging the images together. Then, we can perform mesh extraction, pulling out vertices and triangles from point cloud data. Finally, additional improvements can be made to the mesh, such as simplification and texturing. First, pose estimation. SLAM allows us to align the images into a common space, such that we can integrate them successfully. Once we know the position of a frame, we can combine it with all the other images we've collected so far into some data structure. Once we have a pose estimated image, we need to convert the depth image to a point cloud in 3D space. Assuming we're using a pinhole camera, we use the intrinsic matrix to project pixels from the image to 3D space. The intrinsic matrix is unique to each camera and is a projection matrix from a pixel on the image plane to a 3D ray. We then use the depth data to find the actual position in 3D space. Once we have these point clouds, we need a way to integrate them or merge them together. A naive way of doing this would be to simply combine them into a larger point cloud containing the points from both smaller point clouds. However, this loses the context in which these point clouds are generated. The points are noisy measurements of a common object. Therefore, it is more effective to merge and average the observations of different frames to develop a better representation of the scene. When it comes to integration and a geometric representation to integrate frames into and create a 3D reconstruction from, there are several different approaches, of which we'll talk about two. One uses a list of surfels, or surface elements, oriented disks, to represent space. The other approach is to use a volumetric representation, such as the TSDF, or Truncated Signed Distance function. A volumetric representation means that the data structure represents volume, in a way dividing up the space. Using a list of surfels as the geometric representation comes with certain trade-offs. One of the greatest benefits of using surfels instead of a volumetric representation is the avoidance of the redundant work that the TSDF needs in order to function. Other benefits include the malleability of the surfels. As the SLAM is constantly optimizing its estimations, surfels can be moved around at will much more easily than data inside a TSDF. However, This comes at the cost of being less robust to noise, as well as no longer obtaining manifold meshes. The redundant work that the TSDF needs is depicted in the diagram here. Notice that there are two data structures when running SLAM and 3D reconstruction side by side. The SLAM requires a keyframe map in order to perform its localization. The 3D reconstruction requires a TSDF, in which we integrate new frames into and extract a mesh from. Using a list of Surfels, we wouldn't need the 3D reconstruction data structure and could use the keyframe map and an additional list of Surfels both for SLAM and for 3D reconstruction alike. The TSDF operates as follows. First, divide the space evenly into voxels, or volume pixels. You can think of them as small cubes. Second, retrieve a pose estimated depth image and project its pixels into a 3D point cloud. These pixels all lie on the surfaces of objects. Depth measurements are taken of surfaces, and empty space has no measurements. Third, for each point, draw the ray from the camera to the point. For the voxels along the ray before the observation point, assign a positive value representing the distance to the point measured. For voxels along the ray after the observation point, assign a negative value representing the distance past the point measured. In this representation, when voxels change signs relative to their neighbors, this indicates a surface. As we take more observations, we average out the value of the voxels. In this manner, we can minimize the impact of noisy measurements as each voxel becomes the average of many different samples. Another benefit of TSDF is its performance. Integrating frames with one another happens extremely quickly, enabling real-time 3D reconstruction. Once the TSDF has been filled with observations, a mesh can be extracted. The predominant mesh extraction algorithm is called marching cubes. Marching cubes is an algorithm developed by Lawrenson and Klein in 1987 and uses the following technique to generate a mesh from a TSDF. For each voxel, calculate the plus-minus value of each vertex, where plus means outside an object and minus means inside an object, and perform a lookup based on the combination of the 8 vertices for the appropriate pre-computed mesh segment. There are only 2 to the power of 8 possible configurations for the vertices of a voxel, and many are rotations of others. The major benefit of using marching cubes is its speed, as it only requires 1 lookup per voxel and no other calculations. However, it results in a blocky texture similar to that of Legos, hence the name marching cubes, due to the nature of the algorithm. This is counteracted by later steps of simplification, as well as increasing the resolution of the reconstruction and decreasing the size of the voxels. When simply generating a reconstructed mesh, the complexity of the mesh becomes very large very quickly. For reference, this small section of my house, recreated on the left, has over 4 million faces. For comparison, this scene from Crysis 3, one of the more detailed video games of the past decade, has only 3 million triangles. The reason behind this is the existence of many small triangles that are simply comprising a larger plane. This is due to the process in which our mesh was created. Each voxel, each small cube of space, generates anywhere from 0 to 5 triangles in our final mesh. Clearly, there is some redundancy there. For example, the wall of the hallway in the left image is basically a rectangle in 3D space. This can ideally be represented by only 2 triangles. 2 techniques to reduce the complexity of a mesh are quadric edge collapse and planar extraction. Quadric edge collapse seeks to reduce the amount of faces in a mesh by removing edges and merging faces that reduce the error in the mesh the least. This iterative approach can extract a simpler mesh without too much trade-off. For specialized cases, such as the hallway in the previous slide, planar extraction is a useful mesh simplification technique. The goal of planar extraction is to detect planes in a point cloud, and using this data, we can assign a few large triangles to represent the entire plane. Mesh texturing further optimizes the use of the mesh in applications, easing the process of rendering a mesh. Texturing is the process of mapping each point on the mesh to a 2D coordinate, and then saving the mesh colors onto a 2D plane to be used later. Although not relevant to real-time reconstruction, for incorporation of a mesh into a scene, texturing is very important. One of the biggest hurdles to overcome in 3D reconstruction is the ability to perform the reconstruction in real time. With long computation times and endless memory, offline reconstruction is an art on its own and can be optimized to the point of perfection. However, in real-time 3D reconstruction, trade-offs have to be made for speed and memory efficiency. With real-time reconstruction, new frontiers of AR can be explored. One such application is HoloLens holoportation, Microsoft's technology that brings live 3D reconstructions of people into your living room via the HoloLens. An array of sensors takes measurements of one person and performs 3D reconstruction, sending it to another person's HoloLens, allowing them to interact as if they were there. When dealing with real-time 3D reconstruction, we run into the issue of scalability. When performing offline reconstruction, once the data has already been collected, the extent of the reconstructed scene can be calculated beforehand. During real-time 3D reconstruction, the system must be able to scale indefinitely. In order to achieve this, we perform several upgrades on naive TSDF. One major weakness of traditional TSDF is the issue of rigid space allocation. Because we divide the real scene into voxels of fixed side length, we must decide the overall dimensions of our scene upon the creation of the TSDF data structure. One possible solution for this problem is a hashing function that assigns a value to sections of the real scene, each containing multiple voxels. Each one of these sections can be thought of as its own TSDF. In this way, the scene can grow dynamically as more parts of the scene are discovered and placed into the hash table. This allows a much more efficient and scalable TSDF representation. The implementation we use is derived from the elastic reconstruction system. Another solution to the scalability of TSDF is mesh blocking, where every time the camera has moved a certain distance, a mesh is extracted and the TSDF is reinitialized with the current camera position as its center. In this way, real-time reconstruction can be extended much longer, however, with the drawback that earlier sections of the mesh are now immutable. This also helps with speed, as the size of the TSDF we keep is limited, and we only need to render the older blocks of the mesh. The attachment between blocks of mesh and keyframes is key to the speed increase and malleability of the real-time reconstruction pipeline. The rendering process of previous mesh blocks includes a step that checks each keyframe's position and location, estimated by the SLAM system, and transforms the mesh appropriately. As SLAM continuously optimizes this pose and location, the mesh blocks align more accurately with the real scene. Just as with SLAM, we will peer into OpenARK and see what allows the system to run and provide both real-time and offline 3D reconstruction. In addition to the open source libraries required to run SLAM, which is also used during real-time 3D reconstruction, Open3D is another open source library used for OpenARK. The specific functionality provided by Open3D are the TSDF, the data structure used for integration of camera frames, mesh extraction, the implementation of marching cubes, and voxel hashing, the spatial hashing function used to expand the scalability of TSDF, as well as improve its speed. The SLAM dependencies are also listed here for convenience. The frame data types used in 3D reconstruction are the map keyframe, multi-camera frame, and RGBD frame. The first two are used for input and output to the SLAM system of OpenARK. The final frame data type, RGBD frame, is used for integration of frames into the TSDF. The main workhorse for OpenARK real-time 3D reconstruction is the segmented mesh object. It handles all the functions required for reconstruction: integration of new frames, extracting the current mesh, and performing the mesh blocking algorithm described in earlier slides. Integration of new frames is implemented using the voxel hashing algorithm powered by Open3D. It is run on the CPU and sped up using parallelization provided through OpenMP. Mesh extraction uses the marching cubes algorithm to quickly retrieve a mesh from the current TSDF. In accordance with the mesh blocking algorithm, there is one TSDF data structure maintained at all times. Along with this is a vector containing immutable blocks of older sections of the mesh, each capable of transforming independently when loop closures optimize older parts of the map. Another important class for OpenARK's 3D reconstruction module is the SaveFrame class, used for saving data in order to perform offline 3D reconstruction. In order to perform offline 3D reconstruction, 4 pieces of data need to be saved: an RGB image, a depth image, the pose estimated for the frame by SLAM, and the camera intrinsic, required to project the depth image back to 3D space. This saving of data is crucial to the philosophy behind OpenARK's real-time 3D reconstruction. One of the limitations of real-time reconstruction is the rapidly increasing computation complexity when the resolution of the mesh increases. For consideration, a room constructed at a resolution of 1 centimeter may have millions of triangles, while the same room reconstructed at 3 centimeter resolution may only have 10,000 triangles, a much more reasonable number to render and integrate to in real time. Also, in real-time reconstruction, optimizations to earlier portions of the mesh arising from loop closures are difficult to deal with, and oftentimes expensive operations are required, such as de-integration and reintegration of all previous frames. Therefore, OpenARK's 3D reconstruction module is broken up into 2 parts, an online and an offline part. The online part runs real-time reconstruction at a lower resolution, with the goal of providing the user a visualization of the current scanning progress. The data is saved at the same time, and then the scene can be constructed at a very fine resolution once SLAM has stopped running and the poses have been finalized and optimized as well as possible. The real-time 3D reconstruction demo has the following structure. As with the SLAM demo, first, we initialize a camera object, specific to whichever camera we are using to run OpenARK. Then, the SLAM system, segmented mesh, and GLFW manager objects are instantiated. Callback functions should be passed into the SLAM system. Then, the main loop can be run. When the output of SLAM is received and a pose has been estimated for a new frame, it is passed into segmented mesh for integration. It is also passed to SaveFrame for saving, to be reconstructed later offline. Loop closures are also detected from the SLAM system, and the transformation of older mesh blocks inside segmented mesh are updated accordingly. The following screen captures are the results from our real-time 3D reconstruction algorithm. The code was run on a Microsoft Surface Pro tablet, and the scene was captured in one cursory pass using a single RealSense D435i camera with stereo depth and an RGB camera. The reconstruction required real-time integration, mesh extraction, and rendering. The data was also saved for later offline reconstruction. The integration is run at 10 Hz, and the mesh extraction is run at 1 Hz. One thing of note is that since the 3D reconstructions come from a single RGB camera, gaps in the scene are inevitable unless one is extremely careful about their scanning technique. Also, the backsides of objects in the scene will inevitably be incomplete as they are fully occluded. These screen grabs here depict the difference between real-time and offline reconstruction quality. The image on the left, taken from a 3D reconstruction run at a resolution of 3 cm, exhibits many of the weaknesses of the Marching Cubes algorithm. The surfaces of the scenes are very blocky and have imprecise geometry. The image on the right, taken from an offline 3D reconstruction run at a resolution of 0.5 cm, shows the effect of simply increasing the resolution of the reconstruction on the performance of Marching Cubes. For comparison, the image on the left has 10,000 faces, and the image on the right has 9 million faces. In regards to the gaps in the scene due to imperfect scanning, the solution is the study of object completeness. Recent works, such as this paper, extending deep SDF for automatic 3D shape retrieval and similarity transformation estimation by Oladapo Afolabi, a previous PhD researcher at the Berkeley AR/VR lab, have explored the use of deep neural networks to learn how to fit complete models to incomplete objects in the scene, filling in the gaps that are left due to imperfect scanning. Some future work at OpenARK involves having some fun with 3D reconstruction and seeing where it can be applicable. We have a team working on performing real-time reconstruction on drones, which would require large engineering improvements and considerations such as bandwidth and computing power on board the drone. Another struggle is the performance of depth, both at great distances over 10 meters, and the lack of IR capability as the sun blows out all IR light.